Hello everyone, welcome back. This year we're going to be talking about, this week, we're going to be talking about switchgear identification, how to classify them, what sort of equipment and what their capabilities are that you're going to be running to in the field. I hope this gives you a little bit of context on what you can and cannot do, what things you should be looking for when you see some equipment in the field. We're going to classify things in a few different ways. We're going to be looking at the difference between a load break rated and a non-load break rated switch. What's the difference and why should we care? We're going to be taking a look at 4 different types of insulating technology, where they came from, why each one exists, answering the question, why is there even more than one, and what are the advantages of each. We'll take a look at manual versus motorized and local versus remote. So first things first, when we're interrupting our current flow, if you remember back, we talked about this in one of our first weeks. There's always going to be an arc that occurs right as the contacts break. We've got our switch contacts and they're touching each other, and then as they move away, at some point they stop contacting each other. And because we have a highly inductive system, we end up with a localized voltage rise. And that's going to cause the very small gap between our contacts, the insulating material that's in there, it's going to cause it to break down. And we end up establishing an arc. And we talked about early in the semester that those arcs are hotter than a welder's torch by far. The potential to be hotter than the surface of the sun. And as you can imagine, that would do a job on your electrical contacts. Now, when electrical contacts are closed, they need to have a really good contact right in here. This needs to be very smooth and it needs to be very clean so that the electricity can flow through without having any resistance. If you end up with resistance, you end up with localized heating right at your interface. If things get hot, then a couple things can happen. In your best case, your contacts lose their temper and sort of burn away from each other. In the worst case, your switch contacts weld shut, and now your switch isn't a switch anymore. It's just a hunk of steel or copper or aluminum, and you go to open it and it just will not open. All of these conditions are potentially dangerous and to be avoided. So the other thing we got to take a look at is when we open the switch, there's going to be this arc we're talking about, and how are we going to control that arc? Obviously, if that arc is uncontrolled, that creates a dangerous situation. What if it transfers off of these switch contacts and makes contact with an adjacent conductor? Now you have a traveling arc on the loose, and we saw a video about how devastating that can be in a previous week. So we can't have an uncontrolled arc. So when we're talking about a switch, we're talking about how does this switch, or can this switch, manage the arc? If it doesn't have the ability, and there's our first differential, if the switch does not have means to manage the arc, you can't use it to break load because you'll end up with this uncontrolled arc and kaboom. So our first category, load breaking versus non-load breaking, we now have our answer. A load breaking switch has the ability to control and suppress the arc that occurs when you open it with current flowing, whereas a non-load breaking switch does not have that capability. Now, in my last lecture, I talked about having a fault break rated device, and that was mostly around the idea of reclosers and breakers. And the difference between a load breaking switch and a fault breaking switch is how much arc they can handle. The more arc they can deal with, the closer they become to a fault break rated switch. whereas a load break rated switch might be rated to deal with 600 amps. And, these come in the range of 200 to 900 amp break ratings. A fault break rated switch is going to be good for somewhere around 4,500 through, 60,000 amps of interrupting capacity. So a much larger ability to break the load. And so the difference between that arc suppression, they're going to have to obviously build it using a different design. You're going to need a more elaborate arc trap and an arc snuffing equipment. You're going to need stronger springs to overcome the proportionally stronger magnetic forces, a more robust construction to withstand those forces. And how do you address the idea that you're going to have this incredibly powerful arc? How do you keep your switch contacts so that they're flat and smooth and not cratered and pitted from the arc that they experience? And one of the primary ways that they'll do that is they'll actually have two switches built into one. You're going to have two sets of contacts. You're going to have a primary set, and that carries the load when the load current when the switch is in the closed position. And then you're going to have a secondary set, which is used for dealing with arcs. And so, since those don't carry load when the switch is closed, we can allow them to get pitted and chewed up, and it doesn't affect the operation of the switch because when the switch is closed, they're not carrying any current to speak of anyway. And so here's an example of what that might look like. We've got two sets of contacts here. We've got our primary contacts, and so these are typically a blade, so these will fit into a slot, and there will be spring tension on the front and the back of this, right? And so when it's in the open position, and then we're seeing it again in the closed, so our main contact here, it's going to have springs, it's going to be pinched from both sides. That's going to be silver plated contacts typically because the silver plating is going to resist corrosion and still have an excellent conductivity even if it does get some corrosion on it. And then we're going to have a secondary set of contacts. And in this case, what we've got is we've got this little nozzle design here and then a pin that reaches around in. And when these contacts go to open, this main contact is going to break first. So at some point, what you're going to find is at some point after this starts to move, this becomes open while this is still closed. So that when the arcing contact or your secondary contact finally breaks, the arc is drawn here and there's no arc drawn over here because there's much more space. And so the dielectric breakdown occurs at your arc contact. Now, in this case, what this arc contact is shown here is designed to do is it's designed to contain the arc within this funnel shape here. And then once you exit the funnel, it's designed to swing very quickly and make a lot of space, which will overcome the arc's ability to stay hot very quickly. And so that's how it's going to deal with the arc. It's going to allow that arc to form, and then it's going to stretch it much too quickly for the arc to be sustained, and the switch is now open. And it does that without allowing the arc to ever touch the primary contacts. And so it preserves these and the surface quality on them so that you don't get any localized heating. Whereas this contact here, this tip and this pin, that's going to get chewed all up over time. But that's okay because we only need it to withstand the arc, not carry the current under load. So one special case is your load bust disconnect switch. So here is a disconnect switch in the field. We call them solid blades. And on its own, it's a simple switch. You can see we've got a lower pivot. We've got some contacts up here that the arms slide into. You get your internal contact there. And this whole arm, this has a little locking mechanism. You unlock it when you grab it with the hook stick. And so you'll see these used as inline switches, mid-span. You'll see them mounted to poles. Fuse holders operate on a very, very similar set of principles, although they don't have a locking mechanism. And so if you take a look at this, there's no presence of a secondary contact. So on its own, this switch is not rated to break load. However, what manufacturers have done is they have a load bust tool. And so this is an attachment. It goes on the end of a hook stick. And these upper segments engage with these horns right here. And internal to this cylinder is a secondary set of contacts. So when you're using the load bust tool to pull this open, and this piece here telescopes, it stretches out and gets longer. So once you apply the load bust tool to the hooks and you grab on through the handle and you pull it open, these contacts will swing open at this point here, where the contacts inside this tube are still closed. As you continue to pull, these contacts open up and the arc is formed inside this fiberglass cylinder where it is contained and controlled and extinguished. So as a result, these tools need to be certified on a regular basis. Please check your certification dates. They do wear out, and so these cylinders are occasionally replaced. But that creates a special case where if you have a set of solid blades or a fuse holder and you do not have your load bust tool, you cannot use it to interrupt load because there's no way of controlling the arc. And so this is a conditionally load break rated device. The secondary set of contacts are contained in the tool rather than being attached to the switch itself. There's our distribution cutout, and we can see here's the hooks to attach the load bust tool and a similar configuration between them. So there's 4 different technologies that are used for insulation in distribution switchgear. The oldest was air. It's been around since the very beginning, and air has a breakdown voltage of around 3 million volts per meter of distance. Around the 1920s, when distribution systems really started to move into cities in a big way, they realized that the air brake switches were very large. They needed a lot of maintenance. Sometimes they would have a maintenance cycle after as few as 4 or 6 operations at the time. And so they needed something better. And what they came up with was oil immersed switchgear. Now, oil immersed switchgear was great. This very high breakdown voltage, 10 times that of air, 30 million volts per meter, meant that equipment could be literally 1/10 the size and have similar ratings. But at the same time, it has some drawbacks. Most notably, we've taken electrical arcs and covered it in flammable mineral oil. The oil used in switches is very, 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 very close to what is used in transformers. A little bit of time passes and they realize that oil has too many drawbacks and they're looking for something superior. And they start using a gas known as sulfur hexafluoride, or SF6. It's got some of the benefits of oil, almost 3 times the insulating breakdown value of air, but it's not flammable and it's transparent. So you can see through it and it doesn't catch fire, which is a grand advantage. And a couple years after that, they introduced vacuum technology. Now, vacuum technology is a different technology altogether in how it controls its arcs. had big improvements compared to the oil technology in terms of safety and size. I mean, the vacuum equipment today is incredibly compact and lightweight. It's very nice to work with. And so what you're going to see is that we still see a lot of air-based equipment, like our fused cutout, for example, is an air insulated switch. Same with our inline, it's an air insulated switch. And the reason you see a lot of it is it's cheap. You don't need to pay for the air. It's all over the place. And the technology is very mature. The designs haven't changed in many, many years. And so if you find a fused cutout that's 30 or 40 or 50 years old and the fuse is operated, you'll be able to put in the same fuse that's riding on your truck. If the fuse holder's blown, there's a good chance the fuse holder in your truck still fits. And so that continuity really helps, and the low cost really helps. And so as a result of that, you still see this stuff everywhere. In terms of oil-based switchgear, this stuff is obsolete. They don't really manufacture new oil-based gear in any sort of volume, and you're going to mostly see this in legacy stations at older sites. Gas insulated and vacuum equipment is expensive compared to air-based equipment, but has some serious advantages. And so you'll tend to see it at key switching points. And you'll see that the use of gas and vacuum, they're both prevalent in the industry. They have their own pros and cons. And so depending on which utility and which application, you could see either or a mix of both. So let's talk a little bit more about air. Air-based switchgear, it's got the lowest breakdown voltage, and so this equipment is going to be the largest. Because of the designs, when you're doing maintenance on it, you need access to both the front of the device and the back. Because it's so large, it's kind of unsightly. So people don't like having air-based switchgear on their front yard, for example, or in a boulevard. When we're talking about maintenance, since we're using air and atmospheric air in particular, right? So wind literally can blow through these things if you blow hard enough. They're not sealed. You get everything that comes with atmospheric air, like moisture or pollution. Because these things are open, you can get animals getting into them. And let me tell you, rats' nests don't have the same breakdown voltage as open air does. And the other problem we run into is the arc snuffing functions that exist on these air brake switches are just not as good as newer designs. Keep in mind, we're talking about equipment that was originally designed, load bust arc snuffing technologies originally designed, some of them in the 1890s. 80 years with a serious technology advancement, the arc snuffing technology in these air-based switches is just not as good as what's available on a modern design. The other problem, we got some safety concerns, and this one is really significant and should not be underestimated. This is all live front gear, which means you open that front cover and there is primary voltage right there on an uninsulated termination. Obviously, because of this, you can't put it underground. If it floods, you've got no insulation left at all. Now, when you are using one of these, because there's still lots of them out there and in service, because they're live front design, they're pretty cumbersome to use. And they all come with fusing, which is good, but that's a thing that we need to stock. And because of those poor quality arc snuffers, you're not going to get that many load break operations out of them before it's time to go and clean those contacts up. In terms of SCADA, which was our remote control technology we discussed last week, they tend not to work very well with that. You can do it, but it's expensive, and you've now automated a switch that you can't really use very often before you have to take it down. So not a great use of funds under most cases. But here's an example of an air brake load interrupting switch. If we take a look at the vertical configured one, we've got our main switch and we've got this module here, which is an arc snuffing module. Over here in this design, what we're going to see is this central bar rotates on operation, and you're going to see that this, it's a little bit challenging to see, this little bar here is going to swing out and it's going to ride as this begins to rotate, and that serves as a secondary break point for the contact so that we don't chew up the primary contacts. However, this is still going to allow for a fairly large and fairly uncontrolled arc compared to other designs. For pad mount load brake gear, you're going to find your cables come up and the terminations are here to a metal plate and they're all exposed. They're single phase fusing. The actual switching occurs in the back of this cabinet on the other side of these fire resistant and arc resistant barriers. The term is glastic barriers. Pay attention to these when you're operating them. As on older vintage equipment, these things are usually made out of asbestos fiberboard. Keep in mind, asbestos fiberboard is completely safe to be around. It's completely safe to operate unless you're asked to start drilling holes in it and generating dust. There's no risk from that asbestos. But when you go, if you're ever tasked with tearing one of these down for maintenance or scrapping one out, you might want to speak to your supervisor about what the utility's specific practices and policies are, and if there's any asbestos fiberboard in this particular unit. Moving on to oil-based switchgear. Here we're going to take advantage of that very high breakdown voltage that we get. 30 million volts per meter. So these switches are going to be very compact. The other thing that happens is they're all sealed up. So now we can have pad mount gear and submersible rated gear because now our switch contacts and our insulating medium are isolated, they're sealed from the greater environment. Now, one of the problems we run into is when you have an arc under the oil itself, which is a long chain polymer, it's this big organic um, molecule, right? And so you get this carbon chain, and these will be very, very long. And then you get these powerful arcs, and they'll go and they'll break the bonds. Wow, that was too big. They can go and they break the bonds on this oil. And so as you withstand arc after arc, the oil itself begins to break down. Now, if you guys have ever checked the oil in your car, you'll know that pretty quick after, if you've ever done your own oil change, you look at the oil in the bottle and it's clear, it's translucent, you can see through it, it's beautiful. You pour it into your car, you check the dipstick a week later, and the oil's gone opaque. You can't see through it anymore. It's picked up enough carbon and contamination that you just can't see through it. Now, that doesn't mean the oil's no more good. Certainly, the oil's going to be good for its rated life, but you can't see through it anymore. And so, because we can't see through it, we don't have any visual indications of our switch state on our oil-based switchgear. And when we're doing maintenance, we need to check to see what sort of other chemicals have been formed by the breakdown of this oil, because some of them are pretty nasty. Some of the common side effect chemicals that get formed when these chains break down are acetylene and hydrogen. And so if you have a sealed container full of acetylene and hydrogen, and you expose that to an arc, what have you made? I would say a pretty dangerous situation. You let that go uncontrolled too long, and what you've actually made for yourself is a very nice pipe bomb. So when you have to check for that oil on a regular basis, and you gotta be looking for contaminants, what's our dissolved acetylene? What's our dissolved hydrogen? What other dissolved chemicals do we have in there? Has the thing turned acidic, and is it chewing up the actual switch contents? And it's a bolted gasket. These things are, if you have a square tank with a lid on it, and you'll have a flange down to the housing, and there's going to be a row of bolts all the way along. And this is going to have a rubber or a cork gasket, and those age out, and over time they stop doing their job, which can lead to two problems. One is it can let the oil out, which can leave you with a rather nasty problem for environmental cleanup. And the other problem is it can let water in. And if water mixes with your oil, this 30 million volts per meter that you're counting on drops dramatically and fast and accelerates the failure of that oil and the generation of contaminants, and can even lead to the switch failing entirely. So in terms of our operation, oil contaminants are an issue, and every time we use it, it makes the problem worse. So again, an old technology originated in the 1920s. We've got limited endurance because of this oil contamination issue. And so you can find automated oil switchgear in some select stations. You certainly wouldn't choose it for a modern design, but you will find it out there. Typically, it was very expensive to do, so you won't find it as an incredibly common occurrence, but it is out there. Integra's power lines, we've got some automated oil-based switchgear in some of our substations that step down from 27 kV to 4. Um, Let me know if you have any questions about those stations. So here's some pictures of our oil-based switchgear. So this is an example. Now, one of the things you might have seen is a switch or a handle on the front of a transformer that allows you to do an A or B side selection or a feed through. This is similar to what they look like on the inside. This is a non-load break rated one. You can see there's your contacts, right? So we have a contact, top and bottom. These guys have a little bevel to them, so they're going to apply friction and force as they move past, and there's a simple pin, and there's your in and your out. You've got a bolt hole, very simple mechanism. So this one has no means of controlling arc, so this one's not load break rated. You move on to this guy here, much more complicated to design. This would be something like you'd see inside a pad mount transformer that was switchable. And inside these housings, you're going to find there are secondary contacts. And so now we have arc snuffing. And so this guy here is going to have some load rate break capabilities built into them. This guy here is an example. We've got some oil-based breakers. So this entire tank here, or on the back side of these, this tank here looks like a giant oversized transformer with two primary bushings coming out of it. So those tanks are going to be full of oil. This tank's all full of oil. And so when those guys up, there's going to be a switch inside there made out of a non-insulating material. Of course, if you get into some of the stuff that's really, really vintage, the arms that hold the contacts can actually be made out of wood, which becomes one more, laminated pieces of hardwood. So one more thing to keep an eye on during maintenance is that wood holding up, because it certainly doesn't have the same properties that some of our modern materials would. For our third technology that I wanted to talk to you guys today is SF6, or sulfur hexafluoride. So this really, it was introduced in the 50s, but it really didn't get going until the 1960s. And it was the 70s before it really hit its stride. In 1974, they introduced a design called the puffer pack, was the first one that really started working well. And then they started selling pretty well. And so this technology, although it's 70 years old from its inception of as a technology, it's really only about 50 years old in terms of how long it's seen widespread use. So SF6 is very interesting stuff. In terms of dielectric strength, it's around, 2.5, 3 times that of air. Now, SF6 is great. It is chemically stable. It is non-toxic. It doesn't burn. It's colorless and odorless. You can see through it. But it does have some downsides. It is heavier than air. This is a good news story and a bad news story. Consider it's heavier than air. So if you're in a vault with SF6 switchgear at the bottom, right, you got your manhole access, you've got a piece of switchgear in here, some cables coming in and out, and you're tasked to go back down in there. You better bring your oxygen sensor, because if this piece of SF6 switchgear has been leaking, there's no oxygen down here. And that's a good way to get yourself into a rescue situation. It's heavier than air, it displaces oxygen. The other problem with SF6 is it is a very powerful greenhouse gas. It's among the worst that we've produced, and it's one of the few of its class that's still manufactured. And it's manufactured primarily because of its very niche use. People are still buying SF6 switchgear. It's still cost effective, and for a lot of applications, it's still a very reasonable way to go. Some advantages: it's compact, it's lightweight. The design are from the 70s. Compare and contrast the sort of technology we had in the 70s compared to the 1920s. That was a big 50 years. So the designs are much more modern. The switch components are, and metallurgy, much better. The alignment of the parts as they swing, much better. And so what you get is a lot larger operating times. Maintenance-free design. You put this in, it'll run for 40 years with zero maintenance, and you could get 1,000 load break cycles out of it before you have to pull it out. The downside is it is maintenance free. In order to keep the SF6 gas in, it is a fully welded tank. So there's no access point. There's no gaskets to fill, which is good, but it also means that there's no door you can open to go in and adjust the contacts or replace them if something fails. If an SF6 piece of switchgear fails, you pull it out, you send it back to the manufacturer, and they deal with it, and you drop in a new one. Now, in terms of safety, some nice improvements. It's totally welded. It's all dead front construction. So very safe. You open the access door to go work on this switch. There's no exposed primary. The front of the switch is grounded. Great. And we mentioned here colorless and odorless. So this colorless piece, you can see through it. It's as clear as air is. So they install windows in this switchgear, and you can look in, and now you can actually see the state of the switch. Right? Having that visual open is important. For air-based switchgear, it's easy to do. It's out in the open. For oil-based switchgear, it was impossible because the oil isn't transparent. After a couple operations, it's too opaque. You can't see through it. There's no point in having a window there. With SF6, we get our visual open back, which is a major step forward for safety. Rating for Division 1 Class 1 installations, that's neat. It means you can have an explosive environment on the outside of the switch. And because that switch is so well sealed, there's no risk of an operation of the switch detonating the environment around it. Very high interruption ratings. You can get SF6 or gas insulated breakers, right? 48,000 volts interrupting rating. And because of these high interrupting ratings and the very nice modern switch designs, they don't need internal fusing. They can break that load just on the contacts. They're fully sealed, so they're fully submersible, which is grand. Although if they're in a vault, you do have to bolt them to the floor because if you try to sink them, they will float. And you can mount them in any orientation, which is grand if you're talking about an underground vault situation, because you can stick it to the floor, you can bolt it to the wall, you can even hang it from the ceiling if you really want, and it doesn't matter. So whatever sort of space you have to work with, which in a vault can be at a real premium, you can find a piece of SF6 switchgear that you can mount up there so that you can use that space to your best advantage. So we got some demos of SF6. We're going to cut to a YouTube clip. I will see you guys in a minute. I hope you enjoy.
Yeah. Now, what we're going to do now is I'm going to see if I can make an aluminum boat. Let's get rid of this back there. And put this over here. Yeah, it's not going to be a very good-looking boat, I'm thinking. But what I'm hoping is we're going to be able to float this in the sulfur void. Now, if you would just slide that lid off to one side for me. Just grab hold of this. Just slide it really slowly. You're going to be fine.
I'm really no hero when it comes to this, but we'll do. Nothing can happen?
Yeah, we're just going to take that out.
Yeah.
And we're going to put this in.
Look at that. Look at that.
Isn't
Fantastic.
it amazing?
Beautiful.
Isn't it amazing? Yeah.
Beautiful.
I love it. Now,
That is beautiful.
let me show you something. If I scoop some of this out of here, we can sink the boat. Isn't that great?
Isn't this fascinating stuff?
Isn't it? It's so cool. Science is cool.
Vielleicht nicht alle Kerzen, aber die meisten werden brennen. Und dann nehmen wir Schwefelhexafluorid, SF6.
Aber das
Ich
ist
habe
doch
hier einen ganzen Eimer voll.
Aber SF6 ist doch ein Gas. Wie können Sie einen
Das ist ein
Eimer
Gas. Ja, ein Gas, das ist richtig, aber sehr, sehr dicht mit einer hohen Dichte. Also genauso wie die Flüssigkeit hier.
okay.
Noch nicht, noch nicht. Wir machen es auf und dann gießen wir es raus. Nachher. Also, wir zünden jetzt die Kerzen an. Die Kerzen werden jetzt angezündet.
Die Feuerwehr ist ja informiert. Ja.
Jawohl.
Moment. Jetzt erklären Sie uns doch erstmal, was ist passiert. Also Sie haben dort eine Flüssigkeit runterfließen lassen.
Richtig, die Flüssigkeit ist hier runtergeflossen und damit haben wir die Kerzen angezündet. Und jetzt, sobald die Kerzen alle brennen, werden wir sie jetzt auslöschen mit diesem Gas. Das ist eine besondere Eigenschaft dieses Gases. Es ist nicht brennbar. Das heißt, damit können wir Feuer genauso wie Kohlendioxid zum Beispiel auslöschen. Und jetzt, wenn wir hier so einen Eimer nehmen mit diesem Gas, ich gieße dies jetzt herunter, es sollte wie Wasser herunterfließen und ich hoffe, dass jetzt die Kerzen alle ausgelöscht werden. Also einfach hier runterfließen lassen.
Das ist das Gas, das schwerer ist als Luft und die Kerzen da rein.
Ein sehr dichtes Gas.
Das ist schon mal nicht schlecht.
Fließt wie Wasser.
Okay.
What it's used for in industry is in circuit breakers and big switches because it will not conduct electricity.
Oh, electricity won't pass across.
Yeah, now what I've got here is a 400,000, almost 500,000 volt zapper.
Okay.
It's stun gun. If I turn that on, obviously don't want to touch it. Watch what happens. Goes out.
And then when you lift it up?
When I lift it up, comes back on again. So, this makes a very convenient gas for insulating electrical gear.
Now, what if you breathe it? Will you, is it, well, it's not toxic, though.
It's not toxic, so it is safe to breathe. It's kind of like anti-helium.
Anti-helium?
You know how helium makes your voice go way, way up?
Helium makes your voice go higher, yeah.
Okay, well,
let's make your voice go lower.
If you would, you just
Shut up, it doesn't make my voice go low. Really?
Put your head in there like you would bobbing for apples. Take a big breath. And speak.
How's that? No, wow. John, come over here, William, get way down there. Yes, sir. Get way down there. Hey, Mom.
Why did it...
Welcome back, everybody. The video quality wasn't great. It's a little bit old, but I hope you found that entertaining. So here's an example of a piece of very nice SF6 switchgear. And we can see on the front, we have got hookups here. These are bushings. Oops, don't know why we're using red. So we've got bushings to hook up our cables. Here we have got a viewing window. So that we can see our switch contact positions. Down here we have got a reserve tank. So SF6 switchgear is run at a positive pressure, but it's usually a very low pressure. So it might be running at a positive 3 or 4 psi. And so in the event that we do have a tiny bit of a leak, you know, there's a tank here which contains some pressurized SF6 with a regulator. That'll keep your switchgear topped off. And then, of course, we have a pressure gauge which will indicate that the pressure inside the tank is in the correct range. Always check that before you operate the switch, and get a supervisor involved if that number, if that is not showing where it should be. So the last style of switchgear I wanted to talk to you guys about is our vacuum operated switchgear. Now, vacuum operated switchgear was invented in the 1970s, but it really took until the 2000s before the designs became economical for most applications. So this really widespread adoption So this is very new technology. It's still developing. And the anatomy of one of these, um, you've actually got your vacuum interrupter here. So this is the part that does the interrupting. And the operating principle on a vacuum interrupter is very different than all of our other technologies. So with a vacuum interrupter, in this has inside of it, it's a hard vacuum. So like outer space, like deep outer space levels of hard vacuum. There is nothing inside here. And so because there is nothing inside, when those contacts separate, there's nothing to ionize and there's nothing to break down to form an arc out of. So you can't form an arc where you don't have anything to ionize. Because of that, these vacuum interrupters can be very compact. They don't need to move very far at all to make sure that they're fully open. The downside of these vacuum interrupters in this hard vacuum is there's no opportunity for a viewing window. Some designs will embed a secondary switch in them, maybe up here or over here, and they'll show you a viewing window of the secondary set of contacts, but the vacuum interrupters themselves don't have viewing windows in them. The technology to do that directly doesn't really exist in an economical way yet. Now, because these were designed in the 2000s, something had happened since our last generation of equipment. Computerization has occurred. So all vacuum switchgear is designed for remote and computer controlled. These were the first set of equipment that was designed from their inception around the idea that computers would be helping us operate our system, and that the primary way that we are going to interact with this switchgear is through a computer interface and a push button rather than a manual handle. Now, the other thing that these things will do is instead of having a motor with it that winds a spring and uses that to swing an arm to open and close the switch, here we've moved to a magnetic actuator. These are very precise in their movements and they're very fast. And the only limit to how fast you can operate these is how fast you can feed electricity into the electromagnet. So this allows us to have reclose intervals measured in fractions of a second instead of seconds. So it allows us to do some things in terms of probing a fault that would not be possible with any other style of technology. So we mentioned we don't have a visual indicator on the tank itself. Instead, what we have is tied through the drive assembly, through the magnetic actuator, there's going to be a position indicator on the bottom, right? But that is a position indicator that assumes this entire thing is intact. The other thing is with that design around computer and remote as by default, that means we're going to have instrument transformers built in to measure the flow of current and voltage through the switch. That's going to be available to us on all of our designs. So when you go up to if you ever have to operate a switch, you're going to get to the control panel at the bottom and it'll tell you exactly how many amps are flowing, what's the voltage, and it's probably relaying that information back to a central control panel room somewhere. So here's some examples, and you can see from these examples that these are very compact in their nature compared to the other switchgear styles that we'd seen, which were very large and very bulky. If we take a look at this guy, for example, here, you'll see there's 3 individual switches, and they go back to a central control box when then that'll feed down the pole. And so this is a triple single switch, so it could be operated single phase or 3-phase, but again, whether it's a 3 single phase switches or 1 3-phase switch, that's controlled by a computer. That's done in software. This guy here is wearing some animal guarding. These units out to the side are potential transformers. So you'll find one of these terminates to this side of the switch. The other one's going to terminate to the other side of the switch. And so now it knows what the voltage is on this side, and it knows what the voltage is on this side, which allows the computerized equipment that drives it to have some extra ideas about whether there's voltage on either side. Oh, it can do some software magic there in terms of automatically reconfiguring the system by knowing which side has voltage on it. So if there's an outage over here and it knows that, and it can figure out that there's no fault down here, but there's voltage here, the switch can automatically close to allow energy to flow through, for example. Or if it saw energy flowing through, but it knew there was a fault in this segment and the power went out, it could, during that outage interval, because it is so fast, open itself up, segmenting our system so that when the power came back on, it would flow to this switch, but not through it, therefore isolating only the faulted system downline. So here's an example of one of the units with a viewing window. So for this guy here, the vacuum bottle is actually down here. And this here represents a secondary set of contacts. So you're going to go through, there's your vacuum bottle, and then there's a second switch here, which gives you your visual indication. So it does give you a visual indicator that is trustworthy. It is a visual indicator, but the vacuum bottle down here is the one that's doing all the work. And they come in a whole variety of configurations in terms of ins and out directions, right? So if you were mounting on a pole, something like a Z configuration is nice because you can feed in from one side and out the other. Whereas if you had your switchgear in a vault and you were pushed against the wall and you didn't have access to the back, a C configuration could be more useful. Sometimes if you're dropping, an L can be more useful. Vacuum switchgear can, because of its modern design and manufacturing and how compact it is, you can get your bushings pointing in almost arbitrary directions. Last topic I really wanted to touch on was a little bit about our underground system, specifically braking and non-load braking elbows, and how do you tell them apart and what's the difference? So elbows, we use them in all of our pad mounted gear except our air brake stuff. Even some of the air brake stuff is elbows based. And these elbows can serve as a switching element. You can put a stick on one of these and pull it out, and a lot of our switching cubicles will have places to park the elbows when they're not actually attached. So you can pull the elbow out of here and then hang it from this holder. And they come in 2 different sizes. There's a 600 amp and a 200 amp elbow. And they can come in either a load braking rated, or a dead brake rated design. And these will screw in. There's one common bushing for each size in the back, and then you will screw on the appropriate front to this holder here for whether you want a load braking or a non-load braking contact. And these guys here are, so this is a load breaking elbow and this is a non-load breaking elbow. And these are incompatible. You can't plug this guy into one of these. You can't plug this guy into one of these. They don't fit. And the way that you can tell them apart is by the presence of these two white stripes. So if we take a look at this guy, no stripes, no load break. And this is universal across all manufacturers. So this is a standardized universal nomenclature or way of marking things. So here is the magic that makes the load break elbow special. And what you have here on the tip is a ceramic insert. And this is a semiconductor. Really, it's kind of a fancy resistor. So when we are fully engaged, and so at the front of this pin, you've got your insert, and then at the back of the pin, bonded to that. So here you've got your ceramic, and then you have a silver plated aluminum or copper or something. And so when things are fully inserted, the contacts rest over here on the silver plated pin. As the contacts are withdrawn, they begin to slide along this way as the elbow is pulled out. Now, once they hit the ceramic piece, all of a sudden the resistance starts to climb. And it climbs very, very quickly, so that by the time these contacts slide off the edge of the ceramic insert, the resistance is so high that the current is functionally dropped to zero. And so your load current, as you slide it out, drops off very much in a similar style to the way a current limiting fuse operates to drop your current to zero. So the trick with one of these is go fast. The problem is this ceramic insert really is not very big. And so while you're mid-stroke, while the contacts are here, it's acting as a resistor, which means it is slowing and impeding the flow of current. And all of that is being dumped as heat into this insert. So if you dwell with the contacts on the ceramic insert, you will cook it and it will be destroyed, and it'll probably leave a bunch of carbon inside your elbow bushing, which creates a hazard for next time. So when you operate these load break elbows, if you're breaking load with them, I would encourage you to be very decisive in your movements. The other feature that we have here is under this cap. So there's two handles, right? So this is the open and close handle, or position and remove handle. This is a test cap. So underneath here, there's a capacitive plate, which allows you to identify whether there's voltage present. However, it is a capacitive test point, so you can't really draw any current off of that, but it will allow you to directly measure if there's voltage present. So pop this cap off, and there's a plate under there that you can use for doing contact voltage testing. And then in the event that you're actually placing or removing the elbow on a bushing, you're going to use this upper handle here. So we got some photos of some of these installed. We've got some switching cubicles. This one here comes out of Oshawa. It's in one of their vaults at one of the stations they have. We got another one at Oakville here. We've got a piece of gas insulated switchgear, right? We can tell we've got gas insulated switchgear. We've got our viewing windows present. Our manual operating handles set up for single phase operation. If these were set up for gang operated, there would be a bar across them and a single handle. We also know we got our pressure gauge here. We're in the green, so this switch is ready to go. And we've got our parking stands for our bushings. On this side here, we have got load break rated elbows. So these elbows can be pulled and they will interrupt load. You can see our test points as well, just above. And on the back of this unit, here we don't have load interrupted rating elbows. So no stripes, so these are not rated to pull live. However, they may not be rated to pull live, but the assumption is that the switch would open the circuit for these cables, so there's not a lot of point having a load break elbow immediately downstream of a switch. If you've got to drop load, you'll use the switch to do it. Wanted to talk a little bit more about reclosers and breakers. I touched last week on the difference between them. We'll put some numbers to it this time. We mentioned that the breakers have higher interrupting ratings, 40, they can get them up to 60. And then, the duty cycle on a recloser, much more, much higher, right? It's designed for many, many operations in the field, whereas breakers, they can take a lot more, but they have lower operating they can handle fewer operations before you need to go and do some maintenance on them. Continuous ratings, worth calling out. Hard to find a recloser over 800 amps, whereas breakers can easily be found for up to 3000 amps or above. And the breakers have a rating on them to be able to carry that maximum fault current, so that 40 or 60,000 amps, they have to be able to withstand that for many seconds, not just for a fraction of a second while that hits and they immediately interrupt it, but they need to be able to withstand that for a minimum of 3 seconds. So that's a tremendous amount of force and sustained, whereas a recloser has no requirement to be able to carry that. If they get a big hit, the assumption is they operate immediately. They aren't designed to withstand and hold that in while they have time for a downstream device to operate. So if you imagine you have a breaker and then midline you have a recloser and you get that big fault, that breaker is expected to hold in and give the recloser time to operate. The recloser doesn't have that same requirement, and that relates to its somewhat lighter construction. So in general, we've got reclosers. They're smaller, they're cheaper, they tend to have internal instrument transformers, and they come in vacuum is a very common one. You can get gas insulated ones, but really vacuum owns the market right now for reclosers. In terms of circuit breakers, they're big, they're expensive, they have discrete CTs because of they can be on different size range ratings up to 3000 amps. requires a lot of maintenance by comparison. And they come in a variety of different technologies: vacuum, oil, air, or gas. Um, and so a lot of different technologies out there in the market. Again, oil really not for new designs, but certainly a lot of vintage ones still in service. In terms of your physical construction, they're pretty big, right? So there's an external pad style one. This is one that slots into a piece of switchgear. These things are typically a motor actuated. So unless they're vacuum, um, unless it's a vacuum breaker, and you tend not to see a lot of vacuum breakers, they're still fairly rare and expensive. There's a motor that winds up a spring, and when the trip signal is given, the spring opens a physical arm for you, and then the motor immediately starts winding the spring back up. So there's certainly a minimum time between operations for these while we wait for the spring to wind back up. Reclosers, magnetic actuation, very light, very compact, very fast. Now, one of the other types of reclosers that you will almost certainly see in your career is the hydraulic recloser. These are an old style that's been in service for many, many years, well before the advent of computerization. And they are a shunt device. So they sit in the line is coming, and there's a bushing, and it goes down into the recloser, and there's another bushing, and it comes out from the recloser, and internally it actually feeds right through. And these rely on springs and electromagnets, and they pump oil around internally. And when the fault current comes, the electromagnetic pulse overcomes the spring tension, and it causes a cylinder to move. And if the cylinder moves, it displaces enough oil and causes a pressure rise, and it causes the switch to trip open. So they're a marvelous piece of mechanical engineering. It's important to note that these are not programmable. The way you change the settings on one of these is you get in there and you start changing. If you want to change the timing, there's the cylinder that gets, when things pulse, that fills this tank. If you want to change how long it takes for the tank to empty, you change how big the hole is, the timing orifice, how big the hole is. Um, so, very difficult to change the settings on. If you want to change the time delay, right? So if this trips 3 times, that's going to require a certain set of parts here. If you want it to trip twice, the way you change that isn't programming. You go, you pull it out of the oil, you unbolt the part right here, and you bolt a new one on for each phase with different mechanical properties, and that'll allow you to change your behaviors. So fully programmable, a very clever piece of engineering. You still see these, they're still manufacturing these. As far as I'm aware, no utilities in Ontario are deploying these in new installs, but there are certainly many, many of them still out there, and it's almost certain that you're going to encounter them in your career, so I wanted to call them out for you. Another thing that you might run into in terms of reclosers is S&C has a fairly new product out. It's called a Trip Saver 2, and they took an entire recloser, thank you to the wonders of computerization and miniaturization and how small those vacuum interrupting bottles actually are. They took an entire recloser, the computerized brain, the vacuum bottle itself, and they stuck it into a module that fits in a standardized fused cutout. And that allows the engineers to design a so if you have a little peel off into a subdivision and it's a really bad one for trees, you're getting tons of trees, or there's a bottomless font of squirrels, and they're all determined to get into your lines. Instead of constantly sending crews out to go and refuse or check out this section, or you're tired of blinking the entire feeder because maybe you have a mix of residential customers and a factory that is badly disrupted by those momentary outages, you can take one of these cutout mounted reclosers and mount it at the tap off to that subdivision or that cul-de-sac, and this can do your reclosing action, thus saving your factory from all those momentary outages while the upstream breaker or recloser was trying to probe as to whether it was a temporary fault or a permanent one. So wrapping it up, in summary, what do we got? We've got our 4 different insulating materials. We've got some comparisons on visible break size, whether they're dead front, how flexible they are, and whether they're any good for remote control. Hope you guys have a great week, and I'm looking forward to our review session. Questions, please don't hesitate to get in touch.